Now let's talk about conic sections. Conic sections are special curves that are created by taking a double cone, as pictured here, and intersecting that cone with a plane. If the plane is parallel to the base of the cone, we get a circle. If we have the plane at a specific slant compared to the cone's angle, we get a parabola, and we've talked about parabolas a lot in our class. We're going to be talking about them some more here. A slightly different tilt to that plane will give us an ellipse, and circles and ellipses are very closely related to each other. A circle is just a special form of an ellipse. And if we get a plane perpendicular to the base of the cone, we get a hyperbola. A hyperbola looks a little like a parabola, except it's two branches instead of just one continuous graph like the parabola. All of these curves have some varied applications in the real world. One main example of a parabola, if we take that parabola and spin it to create a three-dimensional object, we get something like a radar dish or a satellite dish. These are called paraboloids, and as light or sound comes in and hits this dish, it bounces to the receiver. And that's how these dishes receive signals. No matter where the signal hits that dish, it's always going to bounce to that receiver. A really interesting property of parabolas. You can also find parabolas in your flashlights. If you have a flashlight and you look inside the flashlight, whether it's an older flashlight with an incandescent bulb or a newer one with an LED bulb, they will have a parabolic mirror inside, and the intent with the mirror is so that one single point of light gets reflected out into a solid beam. And it's just taking this idea of the parabolic dish in reverse. So we have the light here at where the receiver is, and that light bounces onto the dish, onto the mirror, and then it gets reflected out. And it'll get reflected out all in these parallel beams. And that's how we get one big beam of light from a flashlight, even if the bulb is really small. More examples. We talked a lot about projectile motion. So any object that is thrown upward will travel in a parabolic path. Bridge arcs could be represented by elliptical curves. Same with arches, like on an overpass. And celestial orbits are conic sections. Tight orbits around the sun are almost circular. Most of our planets have an elliptical path. And then comets that come in and orbit the sun have elliptical paths or parabolic paths, or even hyperbolic paths. More examples of conic sections out in the real world: sonic booms or navigation pre-GPS use conic sections. So let's begin this section with what we already know, what we've already learned. Back in the chapters on quadratics and on functions, we looked at quadratic functions in vertex form. Y equals a times x minus h squared plus k. The a tells us how the parabola opens, and the h and the k are the vertex of the parabola. Given the graphs of quadratics pictured, can you identify the vertex? We'll take this first one, f of x equals x plus 3 squared minus 4. Our vertex values are coming from h and k here in the function. Remember that we take the opposite of the number in the parentheses. So we end up with a vertex of -3, -4. And if we look at the graph, sure enough, that's the vertex of our graph. Taking a look at the second one, h, k. Remember, we take the opposite sign that's in the parentheses. So that's how we get a +3, -4 for our vertex here. In graph 3, x minus 5 squared plus 3. Opposite of the number inside the parentheses gives us a +5, so we have a vertex of 5, 3. Recall too that if you wanted to recreate the graphs, we could create a table. So knowing the vertex, we can then create a table of x and y values, plugging numbers in and getting answers back out. And then looking at graph number 4, similar idea, h, k, +5 in the parentheses, so our vertex will be -5, 3. Now again, we've seen these before. We've created these equations both with using the formula for vertices, or for finding the vertex. We've done this work before. If I have a quadratic function ax squared plus bx plus c, then the vertex is given by -b over 2a and then f of that number. So we would end up with -b over 2a for the x-coordinate of the vertex, and then our function value at -b over 2a for the y value. Knowing these values, we can then rewrite this same function in vertex form. We can either plug these values in directly for h and k, keeping the same a that's above, or to go from general form to vertex form, we could use completing the square.